Welcome to this deep dive explainer. Today, we're unpacking a really fascinating presentation by Dr. Cheng Tian Li on a topic that literally touches every single one of us, human aging. But we aren't just talking about gray hair and wrinkles. We're looking at the cutting-edge evolution of how we track aging at the molecular level. We're going to explore how scientists are moving way beyond standard tests to measure exactly how fast your body is aging on the inside.
Here's the game plan for today's explainer. We'll decode the epigenetic clock, look at the big flaws in current gold standards, dive into targeted DNA methylation, evaluate 3 hardware alternatives, and finally arrive at an absolutely wild future concept, the digital biovault. Section 1. Decoding the epigenetic clock, the biology of aging. Let's get right into the fundamental difference between the calendar hanging on your wall and the actual cells inside your body.
The core goal of Dr. Cheng's research is pretty straightforward: finding a strategic, cost-effective, and highly scalable way to track your biological age using DNA. Because right now, the industry is frantically searching for a viable method that doesn't break the bank, but still gives us incredibly accurate data about our physiological health.
Think of aging on a dual-axis timeline. On one axis, you've got your chronological age, the strict, relentless march of time. You turn 30, 40, 50. But on the other axis is your biological age, and man, that is highly dynamic. Lifestyle factors like smoking, chronic stress, or high alcohol consumption actively accelerate your physiological aging. They literally pull your biological age away from your calendar age. So your body might be functionally 55, while your driver's license says you're only 40.
So how do we actually measure that? We look at something called DNA methylation. You can think of DNA methylation as a system of tiny biological locks placed directly on your genes. They're chemical markers that physically attach to your DNA and alter its expression, basically turning certain genes off over time. By reading the accumulation of these locks, scientists can see a highly readable timeline of your bodily health. It functions as the ultimate epigenetic clock.
Section 2. Flaws of gold standards. The cost of current tech. Now, if this biological clock exists, why isn't your doctor checking it at your annual physical? Well, the established methods have some pretty severe limitations.
Right now, the clinical gold standard relies on high-density arrays, mostly the Illumina system, and honestly, it's a massive brute force approach. It scans a mind-boggling 850,000 methylation loci, or points, across your entire genome. It then crunches that massive data set through machine learning models to accurately predict physiological age, absolute lifespan, and even near-term mortality risk. It's incredibly accurate, sure, but it comes at a massive cost.
And that brings us to a harsh reality. This gold standard is completely unsustainable for widespread clinical use. Why? First off, the data bloat is astronomical. Scanning 850,000 points yields huge data overhead. And here's the real kicker. The vast majority of those points is literally just random chemical noise, not actual functional aging data. Combine that with prohibitive sample costs and locked-in proprietary cloud ecosystems, and you've got a system that simply cannot scale to the general public.
Which naturally leads us to a pivotal question. If the gold standard is this bloated, noisy, and expensive, how on earth do we actually scale biological age tracking so everyday people can benefit from it?
Section 3. Targeted DNA methylation. Finding the signal in the noise. To make this work at scale, scientists knew they had to ditch the whole genome brute force method and pinpoint the actual signal hiding in all that noise. Historically, sequencers couldn't just see these invisible epigenetic locks. They used a foundational chemical trick called bisulfite conversion. It's kind of like a chemical fork in the road. Treat DNA with bisulfite and a normal, unmethylated cytosine base converts into uracil, but a methylated cytosine, one without lock on it, stays a C. This physical sequence alteration is what finally allowed standard machines to detect where methylation had actually occurred.
But knowing how to read the locks is only half the battle. You have to know exactly where to look. And this is the massive clinical shift, moving from random noise to targeted shutdown analysis. You see, as we age, methylation isn't just random. It predictably piles up on specific areas called promoter regions. When these locks accumulate there, they act like a physical blockade, stopping the body's gene readers and shutting down critical gene expression. Dr. Cheng pointed out that by just focusing on these highly weighted promoter regions, you only need to track 3 to 4 specific points to predict biological age within a super tight margin of just 3.4 to 6 years.
Just contrast those two approaches. You've got the outdated brute force scan, churning through 850,000 points of mostly useless biological noise at a premium price, versus targeted shutdown analysis, a hyper-efficient method tracking just a handful of crucial locks on specific regions to achieve incredibly accurate results.
Section 4. 3 sequencing alternatives. Evaluating the hardware. Now let's pivot to the hardware and see how this builds into real-world applications. Dr. Cheng evaluated 3 distinct technologies that are actively competing to replace that clunky gold standard.
Alternative 1 is QMSP. Its biggest win? Cost. We're talking dropping below $10 a site. Studies back in 2015 proved it can effectively correlate with age and even specific traits like smoking habits. But it has a fatal flaw: terrible multiplexing, meaning it really struggles to test multiple points simultaneously. If you're trying to analyze a comprehensive 300-point epigenetic clock, QMSP is basically operationally impossible. It's restricted to very narrow research.
Then there's Alternative 2, SNOOP. Think of this as the solid mid-tier option, coming in at under $200 per panel. It uses fluorescence and is highly accurate. A massive 2016 study of over 900 participants confirmed a solid 6-year margin of error. But the trade-off here? You need a huge amount of raw DNA input to accurately catch those percentage shifts in methylation, which makes the physical sampling process a whole lot more demanding.
And that brings us to Alternative 3, Oxford Nanopore, representing 3rd-generation sequencing. This is a total hardware disruption. It completely throws out that chemical bisulfite conversion trick we talked about earlier. Instead, it literally pulls a single strand of DNA directly through a microscopic pore. The nanopore physically measures the distinct electrical potential of the DNA as it passes through. Methylated cytosines give off an instant, distinct electrical signature that the machine reads right then and there in real time.
Section 5. Digital BioVault. Future, AI and endless queries. This Oxford Nanopore tech doesn't just change the test itself. When you pair it with AI, it completely shifts the entire paradigm of personalized medicine. The scale of this hardware disruption is honestly mind-blowing. We are moving from massive, lab-filling machines to a sequencer the size of your smartphone that literally just plugs into a laptop. It's incredibly fast, reading over 1,000 bases a minute, and because of its size and speed, it is completely field-ready. In fact, this exact tech has been deployed in rural Africa to map disease outbreaks from a raw field sample to a finalized sequence in under 90 minutes. That is a game-changer.
So, synthesizing Dr. Cheng's evaluation, the Illumina array is the highly accurate gold standard, but it's totally unscalable and expensive. QMSP is cheap, but way too limited. SNUP is a great middle ground for custom panels. But Oxford Nanopore, reading electrical potential across the whole genome cheaply and portably, that is unequivocally the future. But it comes with one massive catch. It desperately needs advanced AI.
That catch is the bioinformatics bottleneck. Nanopore outputs these massive raw text files that are literally billions of bases long. Trying to find those 3 or 4 specific aging loci manually is mathematically impossible. The solution? Advanced vector mapping. The AI instantly converts those biological text sequences into geometric directional moves on a grid. Up, down, left, right. By crunching these spatial trajectories, the algorithm can instantly mathematically locate precise deviations and calculate methylation ratios in a fraction of a second.
And this is what unlocks Dr. Cheng's ultimate vision for the future of biological tracking. Sequence once, query endlessly. We're transitioning away from a chemical paradigm into a purely digital one. Imagine capturing your complete unadulterated epigenome via nanopore with just one single blood draw. That physical test is done forever. The data goes straight into a digital vault. Year 1, you run an aging clock filter. Year 2, a brand new cancer marker drops. You don't need a new blood draw. You simply run a new digital filter against your archived file.
Sequence once and query endlessly, transitioning from a chemical to a pure digital paradigm. Just let that sink in for a second. By moving from physical chemical assays to pure digital queries, your biological roadmap becomes permanent, searchable software. So I'll leave you with this provocative thought. If your entire biological footprint is digitized and securely stored today, what new, life-saving secrets of human longevity will your digital BioVault reveal tomorrow? Thanks for joining me on this explainer, and we'll catch you on the next deep dive.